Hello all, I'm Evan Krell and we are looking at autonomous water surface vehicle metaheuristic mission planning using self-generated goals and environmental forecasts. This work is part of an ongoing effort to develop an autonomous surface vehicle explorer. The core idea is that the robot is not explicitly told what to look for. It uses onboard data-driven techniques to select goals and autonomously navigate. These are the core concept for the vehicle. First, it is data-driven. Data may come from online sources such as satellites or other vehicles or directly from the vehicle's observation history. Based on characteristics of the data, the vehicle should assign reward to locations on the map and select some high reward regions as targets. The major theme of this project is that the processing is on board. It should be able to incorporate updated data and regenerate the reward and targets. Another aspect is mission planning, or how to actually navigate to those targets. Environmental forces act upon the vehicle in the marine environment, such as water currents and wind, so energy-based rather than just distance-based optimization is performed. For example, the middle column image shows a path that goes up at first to then take advantage of stronger water currents aimed at the target, instead of just taking the shortest distance path. Another aspect is reactive behaviors. For example, if the boat's camera has been seeing nothing but sand and seagrass for a while, it would be great if it could detect an outlier like these fish bones and automatically pause the current mission and do some local exploration and collect more data of this potentially interesting event. And collision avoidance is required to operate in the highly dynamic environment that includes marine traffic, variable depths from the tides, that sort of thing. This presentation focuses on progress in the data-driven and mission planning aspects. Here's an overview of the system being developed. We've divided it into 3 autonomous roles: the analyst, surveyor, and navigator. The analyst handles data processing and determines targets and reward. Here, there is a history of data that is used to drive the reward assignment. This history is periodically updated with the results of onboard classification. The surveyor is responsible for the actual mission planning, like path planning. It incorporates maps and weather predictions to plan routes to reach targets. Coverage paths take place at target regions, and go-to paths are the sequence of waypoints to get there. Finally, the navigator handles the actual waypoint following control and collision avoidance. Currently, we are working with a Pixhawk autopilot for the controller and have some early work in monovision collision avoidance, which isn't really discussed in this presentation. First, let's consider where targets come from. The system is based on the idea that a map, some kind of raster, is available with the presence of various entities. What are these? They could be substrates or seagrass meadows, habitat types. They could even be just labels of uncertain regions that need exploration. Sources of this kind of information could be satellite or aerial imagery. We've considered a companion unmanned aerial vehicle that gives a course map, which then the USV gets some initial regions selected, but then it gets that higher resolution data using its underwater cameras. But mostly we focused on the idea that the USV's past missions are used to drive its future missions. This means that coverage will be very slow compared to that of some airborne system. The Explorer should be able to take in new data and very quickly update the reward and targets. This reward is based on data characteristics and varies based on the application. For our experiments, rarer entities are given more reward, as well as regions that exhibit greater dynamics in terms of the speed and acceleration of these entities based on their growth and decay in local areas. Algal blooms are an example that would be reasonable using just satellite imagery, since it's relatively easy to monitor from space, that they show up very well in images. You can imagine clustering algorithms detecting the appearance of highly dynamic clusters and setting targets to investigate them. Here is a simplified example. The paper goes into a bit more detail, showing how a quad tree can be used to turn these into coverage path regions, but here, the map of entities at 3 times is shown. The islands are brown, and 2 generic entities are represented by the green and red cells. The 4th figure shows the reward assignment, where darker indicates higher reward. Basically, we are interested in the dynamics of a region rather than a single pixel. So the space is divided into a grid to calculate the speed and acceleration across a recent history. Each cell in the reward raster gets reward for the presence of the entity weighted by its relative proportion. We want rarer. and gets reward for the dynamics of that grid region. You could certainly imagine a smarter, more complex scheme, but again, the goal is speed. If new information comes in, want retargeting as soon as possible to make sure we target possibly short-lived dynamic events. With a 1,000 by 1,000 raster, new updates are handled in under 0.1 seconds. Also, since these maps may be built with the USV's own data, it'll be a long time before the volume of data is available for really getting good results from some of the more complex algorithms. So an obvious caveat is the arbitrary placement of grid lines. Even if we're using quad trees, it's always rectangles. We'll revisit the question of where these entities come from later. For now, let's turn our attention to mission planning. First, the plan should take into account forecasts of weather. We've been working with water currents, but any kind of vector field such as wind would be supported. These change in time and water current models are available for parts of the U.S. coast at varying resolutions with 48-hour time frames, typically at 1-hour intervals. The waypoint should be set to avoid opposing currents and take advantage of useful ones to minimize the robot's applied force to maintain a target speed. Also, on the way to visit a target region, you might have nearby opportunities to collect additional data, thus reward, by slightly deviating from the optimal route. The path planner proposed does so with a weight to tune the influence of the reward maximization component. Again, the theme is fast onboard planning, even if this means not achieving a global optimum. Specifically, the planner exploits the fast premature convergence observed in tests using metaheuristic algorithms for generating the waypoints. After a certain number of algorithm generations, the boat starts using the path. This path continues to be improved while the boat is underway. The fitness function evaluates a sequence of waypoints. This figure shows a single path segment. All the cells along this path are used to total the applied force required given the influence of these currents. While evaluating the cells, an estimate of the elapsed time is incremented as it goes along to estimate the force at that time. The planning results in this presentation are from particle swarm optimization, even though we did tests with genetic algorithm, differential evolution, and artificial bee colony, because we found this converged faster to a local optimum than the others. The paper includes some comparisons. Here is the environment used for planning experiments. A raster of Boston Harbor is selected because of the number of islands serving as obstacles and the readily available water surface currents from the Northeast Coastal Ocean Forecast System. Planning experiments will take place between these currents at time 0 and an hour later, always interpolating between the two. And here are 4 simulated entities. The paper mentions using a large number of maps generated with cellular automata, but the presentation here focuses on these 4 hand-drawn maps, make it a little easier to visualize. After the planning experiments, we'll look at some initial experiments in getting these from real onboard classification. Here are some results with PSO for energy minimization. For comparison, a shortest distance path is also shown, as well as A star using the work minimization cost function. Here, A star is performed on a graph with 8-way neighborhoods, so even though the result is optimal for the graph, it is limited by the jagged paths that these constrained angles produce. PSO can place the waypoints anywhere. Its limitation is that the number of waypoints is an input to the solver, and here we had it use 5. The PSO solution paths show the result of 16 runs. You can see that the 2 general local optima are commonly chosen with a couple outliers. Other than these outliers, PSO performs better than A star in terms of the distance, duration, and work. The red line in the box plots is the A star paths measurement. This A star solution took about 130 seconds, where each generation of PSO takes 1 second, and the convergence curve suggests convergence actually around 130 seconds. However, A star has no path available until reaching the final solution, where with PSO, we have paths every second. In every experiment with PSO, after 10 seconds, the path is headed towards its final solution. That is, it's not, for example, going to jump to left to an island if its original was right of an island, right? So it's already on the right path. So while it's stochastic and maybe this is possible, our experiments have never seen this happen. Typically, this would be considered a weakness of PSO because once it's found a local optima, it never really escapes to find the global. However, here we like that we can get a usable path in roughly 10 seconds. This second set of results with another start and stop location shows similar behavior, Here, PSO is not dominating A star quite as clearly. A number of outliers are present in the set of 32 experiments, and the time to convergence is rather long. However, the basic desirable property remains. The paths are sensible, comparable to A star, and after 10 seconds is usable as an initial solution for the boat to begin its navigation. And here are some results incorporating reward. The reward has been assigned using the algorithm previously discussed on the 4 entity maps. Darker purple indicates more reward. It's relative, so the darkest has a value of 1. They're normalized, and the results on top are 8 runs with the reward weight of 0.1. With just a little influence of reward, it gets more than the shortest distance path while also showing substantially less work. The bottom results are after increasing the reward weights. The reward is higher, but of course, so is the cost of the work, right? Interestingly, I've noticed that when we introduce the reward maximization into the fitness function, this speeds up the PSO convergence. Finally, we consider how these ideas can be used for a real application. So far, we assume the existence of an entity's map. One approach, as we said, is aerial. Here's a high-resolution image of Corpus Christi Bay and Sunset Lake. Near the authors are Texas A&M University Corpus Christi campus. An initial k-means cluster definitely shows clusters, but not all are immediately useful. Some do represent seagrass meadows, but others are just because of a difference in depth. So not really that interesting. So an idea is to use this as an initial highly uncertain map that the USV can use to explore and drive down the uncertainty. We have done experiments where a GoPro Hero 4 is placed under a USV to collect data for online classification. You can see in these samples the water tends to be very turbid. It's a bit of a challenge for image processing. Corpus Christi is a fishing destination, definitely not for diving. To deal with the turbidity, we implemented an image enhancement pipeline, again, with speed as the main concern for classifying the GoPro images. The main steps are white balancing, followed by adaptive histograms as shown. This brings out the details. Initial classification was really just to see if it's viable given the strong turbidity present. Classifying as either seagrass, sand, or unknown. Unknowns could be interesting outliers or really just where I had trouble discriminating. Classification tests with around 3,000 images show accuracy of 82%, but the shallow water missions are set up where each pixel is assigned with a consensus of multiple images. Since I was present with the boat, I checked the map results, and a visual estimate, I think, is about over 90% accurate, which I consider good considering the challenges and the relatively small data set. It's certainly good enough to motivate further work in this area. In conclusion, the analyst can rapidly produce sensible targets in the field with just a few historical maps. The surveyor's mission planning balances efficiency and reward. Outliers exist since it's stochastic, but the speed of the results is promising. Given these are Python implementations, which have room for computational enhancement. And finally, there are real-world classification results that suggest that the concept of building maps from its own data for data-driven analysis is viable. Thank you very much.